Okay, so I'm going to talk to you a little bit about my journey through learning about graphs, databases, and looking at possibilities for them to provide solutions for really difficult real-world problems where we find limitations with other kinds of technologies. So I work for a company called KCOM, and I'll introduce not too much, just a couple of slides on them and about me. The challenges in looking at transport, especially railways, but also the same kind of approaches could apply to airline travel or any kind of public transport, really. Some solutions that we're looking at developing with our various customers, and why we selected to work together with Neo4j on some of those solutions. I won't go into any particular use cases of any customers for obvious confidentiality and commercial reasons, so it's quite a general, sort of my personal eureka moment, as someone said earlier, about using graph databases. So KCOM, a reasonable-sized company, probably not heard of them if you're outside of the UK, because they're only based in the UK, up in the north, in Hull. The Hull this year is the UK City of Culture, which they're very proud of, and my company KCOM is one of the sponsors of that. So if you do want to visit the north, I recommend you go and have a look at Hull. It's quite a nice place. They also sponsor Hull City Football Club's stadium, the KCOM Stadium, but the least said about that, the better, I think, at the moment. I work at the base down in the, just above London there, Ipswich, which again you've probably not heard of if you're outside of the UK. And our main sort of development centre, and I work in architecture and consulting, so we're based out of Ipswich mainly. We've also got offices around the country. And what do we do? Well, our core business was really around telecoms, contact center, collaboration, that kind of thing. When AWS Cloud came along, we also joined AWS Partner Program and became the first premier partner in the UK. So we've been around working in cloud since the very beginning, really. And that is probably most of what I do is based on the cloud, especially AWS, but also Azure and other places. I'm a solution architect, so I work in the architecture practice. We do a lot of integration, digital. We've worked with all the traditional databases, SQL Server, MySQL, Oracle, and the latest addition to that is Neo down there. So this is more personal about me. I describe myself as a bit of a geek. I was actually a farmer in Devon for a few years, and then I got a Sinclair ZX80 computer kit, and you can tell by the name of that computer when it came out, and that got me into programming in BASIC. Later on, I got the programming bug, so I learned C and Pascal, and a language called Prolog, which is a logic language, and in some ways the computing you do with Prolog is very similar to Cypher in some ways. It's you have a knowledge base of facts, and you query the facts using Prolog. So after I'd finished being a farmer, which didn't take very long, I went to university and studied artificial intelligence. So I was a student of AI, and this picture was the first AI system I developed, and that's actually me on the right-hand side there. From Computing and Mathematics magazine, the only time I've been on a cover of a magazine. It's not quite GQ, but it's my claim to fame. So most of my working life I've spent working in IT, if not all of it, I suppose. Mainly in the mobile sector. I worked for O2 for a lot of years, so I know a lot about the telecoms type of use cases that people have been talking about. And lately, for about 5 years, or probably longer, in the transport sectors for British Airways, Emirates Airline, various rail companies as well. I am a Neo4j certified developer, it says architect there, because I don't call myself a developer anymore. I don't develop code, but the actual qualification is developer, I think. But so, transport ticketing, very complex business, but actually boils down to a few key activities. So for the business, the first thing you need to do is model their offering. So model the type of services they want to offer. And in the rail industry, that's modeling, for example, the actual trains themselves, so the number of coaches on a service, number of seats in each coach, the class of the travel, that kind of thing. Also, obviously, the products. You need to model what price of tickets, what the timescales, the origins, the destinations, all that sort of thing. Then you can publish those as into your shop front, if you like, and people can come along and see what services are running and buy the products and use them. And the more sort of underlying services, you've got things like lots and lots of reference data. So lists of locations, lists of products, lists of different kinds of reference data that's used in all these calculations and so on. There's a lot of reporting goes on, a lot of reactive monitoring underneath the scenes as well. For example, if a train is running late, then these alerts go up, and a lot of you will probably have the mobile apps that will alert you that your train is running 5 minutes late, that kind of thing. So if you think about it, there's a lot of complexity behind the scenes of doing something as simple as catching a train and taking a journey. So some of the challenges, as I mentioned here, for those of you outside the UK, we don't have a nationalised rail industry here, at least not at the moment. And in the 1990s, around about 1993, it was privatized and became segregated into different regions and is run by franchises and businesses. There's about 23, 25 of these businesses. And also attached to that, there are ferry companies, so you can see around the coast. These are the main sort of rail lines through the UK. And around the side are the ferries as well. And so the retailing of products, the retailing of systems has to deal with, by law, after that privatization went on, has to be able to deal with buying a product to travel from any point to any other point and include the travel by ferry as well. And the complications behind having different kinds of tickets as well. So the traditional paper tickets that you probably have bought and used, as well as mobile tickets, barcodes, and now you can get smart cards as well, which are special in the UK, ITSO smart cards, which stands for Integrated Transport Smart Card Organisation. And those are the ones that you can get branded by one of the rail companies and travel on the networks. The scale of the thing, as I say, is quite difficult to comprehend sometimes. There's more than 30,000 reservable services run every day throughout the network, and 1.7 billion passenger journeys per year are taken. I mean, it seems obvious when you look at it now. It even looks like a graph, and the data challenges in there lend themselves to graph technologies. So, as I say, it was privatized in the 90s. Systems began to be built in the 90s as well for retailers and the train companies themselves and others to use. And it's in dire need of modernization, and there is a whole modernization program going on. However, there's a lot of tight coupled integrations between all the different retailing ticket systems and the vending machines at the stations and things like that. They all use these APIs. The APIs are very fine-grained, or tend to be. They also tend to be sort of oriented around individual fine-grained entities. So they don't really lend themselves to the more richer kind of queries that retailers today want to make. They want to make the kind of queries of, oh, my friend is traveling to here, I want to also travel to there, and coincide it with my journey. All those sort of more complex queries, just not possible with the APIs. Some of the other challenges are there is personally identifiable data in some of this, especially, for example, if you're a wheelchair user and you need to register to have help at a station. And there's a lot of legislation around data protection that needs to be considered when you're looking at these systems. So this is a bit about why I thought Neo would be a good solution for some of these things. So there's some really good load CSV or load type of functionality, so you can load data into the graph database. There's extra add-ons such as Data Bridge, which can relate the data together as you load it in, even though it's flat files of each of the entities. And what we want to do is design newer, richer APIs. So we're not restricted by the underlying data models in the flat files, and make it more kind of graph-friendly to traversing and loading in the data. So adapting, and also because we have to be backwards compatible with all the APIs that are out there, if you're going to replace the system, then we have to have adapters to adapt those existing legacy APIs to maintain the backwards compatibility. And for data protection, because sometimes you want to actually segment that data off, it's good that Neo can lend itself to working in a polyglot environment. So we may store the actual personal data in MySQL or some other repository, even more secure repository, able to manage the data protection aspects. So another really critical part of any kind of transport ticketing for the people offering the products is to manage their demand. So to sell the right products, to maximize revenue effectively, so sell the right price at the right price, have enough products, and also timely. So you can, a bit like the airline model where you can book a seat well in advance and you get a cheaper ticket than you do if you book on the day. With the train companies now want to move more towards a much more flexible model where they can see how many products they've sold on each service and gradually move towards something where you can flexibly update your products and your prices. And again, that needs to ripple through a lot of services if you want to do bulk updates and that kind of thing. The data model around yield and demand management is complex, because if you've only got a limited number of capacity, then that capacity can be between one calling point and another, and then different capacity between the next calling point and the next. It's not like a plane where you get on at one point, you go the whole journey, and you get off at the next stop. Trains are much different. So the way to manage all that complexity is through having a thing called a nested, so you group the products into groups, and then you can nest those groups of products into things called nests. Whenever I think of that, I always think of a bird's nest, but it's not quite a bird's nest, it's more of a hierarchical network of products. And that, again, lends itself very well to graph technology. In fact, it's a sweet spot for graph technology to be able to say, well, you've requested this type of product, but that's not available, but these others that are very similar are available. Again, there are systems already in place which you need to be backwards compatible with. So the decision support systems today work on quite a file-based interface, so we have to make sure we, again, have adapters between that file-based interface and the graph. And very important is the train companies want to do what-if modeling. So what if I change these yield models to be something like this? What would be the effect on historical sales? If I reran historical sales through this model, would I make more revenue, less revenue, that kind of thing? And because this part of managing the transport ticketing is very strategic, very important to the individual companies. As I said, they're all privatized companies now. In a way, they're all competing. Then it's very important to have a database that can secure that off and make sure that it's only accessible to the right people. So we're very interested in the new role-based access that's been added to Neo in 3.1. Currently, we have a separate identity and access management, which manages role-based access, but there's a lot of benefits in actually including it within the core database itself as well. So that's one thing we'll be looking into. Reporting covers a whole multitude of sins. One of the main things is that every single service that runs, if it's a reservable service, then you want to be able to tell the guard responsible for the service how many people are on that train who might need assistance, that kind of thing. And there's also printing, the old-fashioned printed labels that go in the back of the seats. Those are what we call operational reports, those kind of things. And they have to be generated right up, almost up to the minute before the train leaves the station, some of those. And in future, because we're getting more modern trains on the UK network, they'll have updatable, reservable displays on the back of the seats or in the seats themselves. So not only will you be able to reserve a seat from the start of the train journey, but also part way through as well. What happens if there's someone already sitting in that seat when someone else reserves it? We're not quite sure at the moment. As well as that, there's the more traditional kind of reports need to be generated. How many products of which type were sold during the last month, and that's something that we're actually looking at using data warehouse for. So we have a feed from Neo4j into Amazon Redshift as the data warehouse. So that there's adapters for that. Of course, it's a totally different data model, so there's challenges in itself. Just as there's a challenge migrating current relational data into the graph format, there's also a challenge when you want to adapt the graph-type data to feed into a data warehouse. And that's something that we're looking at using Amazon Data Pipeline and technologies like that to help with. Now, a lot of the companies have also said they want to do more data analysis and analytics on the operational database, which we said is fine because we can have a big read-only replica and attach using ODBC-type service to that and use tools like Tableau or Jaspersoft or some of those kind of reporting tools to access the real operational data. More interestingly, we're also discussing more of the visualization aspects of tools like Lincurious, of visualizing what's going on in the network, especially if there's disruptions, cancellations, that kind of thing. And the final one, which is a really interesting challenge, is streaming. So if one company decides to make lots of new products available on a service, the retailer would like to know. And what the retailer would like to know almost straight away, that this change has happened on a service. So what we're looking at doing there is adapting any update to Neo so that it triggers a stream update to the subscribed retailers. I'm using Amazon Kinesis for that. See, I told you with a lot of Amazon cloud type technologies involved. Okay, so there we go. So Amazon Kinesis, dedicated read replicas for serving operational reports, and for no real reason, there's a picture of my chicken. Monitoring, yes. So obviously these kind of services are really, really critical. They're almost like critical infrastructure for the UK. And if something like the National Rail Inquiries website or mobile app isn't working for a few minutes at a time, that becomes a real problem. So we have basically 100% availability targets. Yeah, you can say it's 4 nines, 5 nines, whatever, but it's basically we've got to be up 100% of the time. Also, if there is a disastrous failure, our RTO is 30 minutes to recover. We have to be resilient to network issues. Those of you who know Amazon, though it's in 3 availability zones, you can lose a zone, for example. You can also lose connectivity between zones, so we have to cater for all these kind of scenarios. Redundancy built into components is sort of just, resilience 101, really. So it's a horizontally scaled read replicas, that kind of thing. Because we want consistency across the services, we use a lot of automated build and deployment technologies, mainly CloudFormation to build out the Amazon infrastructure in the first place. And then we use Opscode Chef to deploy all the various items of infrastructure on top of that. And that includes Docker containers for the services, both at the presentation layer, using Angular, and at the application layer using Spring Boot and Java services. And the performance of some of these things is also critical because people are browsing, looking for the most appropriate rail product. They don't want to be waiting minutes or seconds for the results to come back. They want the results really quickly. So with SLA targets of less than 30 milliseconds per read. And this is on, let's say, the quite fine-grained APIs that are in place at the moment. So you're literally saying, what product can I get on this? Can I get this product on this service? So it's a yes-no, almost a yes-no answer. And scalable to something like 10,000 TPS. So scaling out the read replicas is very important. Even the writes for making a booking and so on need to be very, very fast. So we've got thousands of client systems, thousands of retail systems making bookings, making inquiries. It feels sometimes a little bit like we're climbing the north face of the Eiger there. When you're trying to architect these kind of solutions, it's very difficult. So I said earlier, the rail network looks a bit like a graph. So there's a very simple example of a graph, and all it is a set of locations linked together by a simple relationship, the next along the line. So that's where we started. We gradually built it up, and so now we've got a highly relational, highly complex data model. I'm sure some of the team are here today. They'll back me up on that. It's grown to be very, very complex. However, you can't solve everything all at once. We break the problem into different bounded domains. We use the classic sort of domain-driven design type architectural approaches to this. And we break it down into core, retail, yield, inventory management, those sort of things. And in that way, we're able to gradually build up our model, we gradually build up, and we start to test. And around that, obviously, we have to put all our monitoring and alerting and logging and all that sort of thing. So each of those is autonomous components. They're all tested individually before they're integrated together. We have continuous integration running using Jenkins. As someone mentioned earlier, it seems to be the de facto integration tool today. And have to do all the load testing and so on as well. So why do we choose Neo4j? I think I covered quite a bit of this before. Just to reiterate, the data model is highly relational. And some of the relational databases that we have created ourselves or other people have created are absolute nightmare of foreign keys and relationships, and the queries that you have to run, multiple joins, and the kind of response times we're aiming to get are just absolutely impossible with any size of relational database. Another choice for choosing Neo is I really like the fact that writes are ACID transactional. If you make a write, you know it's going to be there, because the last thing you want is 2 people to book the same seat and have a clash and have to sort that out. The scalability was an issue for us, I think, when we first looked at Neo 2 or 3 years ago. And the reliability, to be honest, it wasn't enterprise ready 2 or 3 years ago when we looked at it first, but it's got to the stage now, and especially with 3.0, where we've got really good architecture now around the clustering, the failover, and the reliability completely. I mean, we've not seen any problems with reliability of running against Neo 3.0. And we also have GraphAware, who we're working with. They're in the foyer out there. Shout out to Vince, who's been working with us. And they're agreeing to provide us support. They've trained us and helping us out quite a lot with this because they are the experts in Neo4j, apart from Neo themselves, of course. So how do we validate all these things? So we built a cluster. I think that was on the previous version. I think it was 2.6, I can't remember exactly. And we did a very early load test on a very simple data model. When I say simple data model, it was still scalable. So the first test was on the simplest database you could imagine, 2 nodes with 1 relationship, and we got response times, not surprisingly, less than a millisecond. Great. We then generated a whole load of data using stored procedures, got up to somewhere like 150, 200 million nodes, and similar, greater number of relationships. Adapted our load tests so it was not just always querying the same node, it's working across this very simple data model. And we still got less than 3 milliseconds reads 10,000 TPS. So that kind of gave us a good feel very early on that what we were trying to achieve was feasible. And now we're at the stage where we want to start our full-scale automated load testing on something a bit more realistic, because we've now done the analysis and built some of the data models for this. We want to look at causal clustering because of our 100% uptime. However, we have a few kind of concerns around the write performance. Obviously, if you've only got a single master and you're writing to it, that's going to be fast. If you have to write out to more than one node in a cluster, that's bound to affect your write performance. Another thing which was, I should say, a little bit of an annoyance, more than anything else really, was even in the master-slave, master-follower type scenarios, there's no simple way to monitor the lag of the replicas, the replication lag. We had to do some clever stuff to actually calculate how far behind the replicas were. And if you're doing, and I know now you can do, write your own reads with causal clustering and all that sort of thing, but the volume of reads we're doing, I don't think we ever want to do causal clustering for all reads. It's eventually consistent is good enough for a lot of the requests for reads, but we do need to know how far behind the replicas are lagging, and it would be really nice if anyone's out there from Neo could give us a simple way of monitoring the replication lag on each replica.
3.2.
Okay, I should read the docs. Great. So we're also using, for upgrades, an approach which I think probably any architect in the room is aware. It's called blue-green, where we build one set of infrastructure, and we call that the blue. We're running on that. Build the second, and that's green. And then test that works, and we migrate across from blue to green, shut down the blue when green's happy, and then we migrate back again. Our aim eventually is for 0 downtime. Now, we know that's not possible at the moment because you can't keep the 2 different versions. Say you're upgrading from 3.1 to 3.2, you can't keep the 2 database versions in sync. There has to be some upgrade, some downtime while you migrate the data. But our aim eventually is for 0 downgrade time. We could do that for reads because the writes could be queued in a queue and applied a bit later or something. But anyway, these are the kind of challenges we're looking at in our work with transport networks generally and rail especially. And thanks very much for listening. I hope it's been vaguely interesting.